So, we will do a small example just to illustrate what we are doing. This is all there in the PPT, you can go and look at it and just look at. So, we want to look at SO2 emission from a stack. So, this is what we want, estimate SO2 concentration at ground level, center line 50 and 500 meters from the stack. So, there is a stack here and we are looking at a distance 500 meters from the stack and we want to know what is the concentration. Center line at ground level, which means y equals to 0, z equals to 0. The equation now this becomes rho A1 500 0 0 60. The height of the stack is 60 meters, it is already given to you. What we mean by height of the stack is h equals hs plus delta h, plume rise, all of that is added and given to you. If you do not have it, you have to calculate all that and then put it there. So, the data that we need is q is that is given to you is this q is 160 grams per second. Each one of this you have to if you do not know anything about this problem, you have to compute all of this individually, including this u, and we are given that it is overcast conditions, and from the overcast conditions from the table, Pascal-Gifford's table class, I calculate that overcast slight insulation stability class is D. So, this is a matter of judgment. So, I think some of you may determine this as stability class C, some may be doing it as D, therefore, your numbers will be different. So, this is an estimate, it is not the true value, because there are a lot of other factors that will. Gaussian dispersion model is an ideal model, everything is very symmetric and all that. There are non-idealities in system in transport that will occur, which you have to take into account. So, based on that. So, we use the so we are looking at x equals 500. So, which means that the computation of sigma y at x equals 500, we take this as 500, this is 500 meters. We go to stability class D, so I am saying the stability class D here, and this line is stability class D, and then I pick my value for sigma y as 36 meters there. And similarly, I do this for the this thing also, the 500, and I am going to this line and I get the value of the sigma z as 18.5. So, if the stability class were A, then my value of sigma y would be around 150 or 120 or something like that. So, I have all of this, I put it in there and I get a value of 66 micrograms per meter cube of SO2. This is the concentration at that point. This is a single computation. So, computation for one coordinate, one point, one location, anywhere around the source, it could be anywhere around the source. Hopefully, it is in the direction of wind. So, that is you have to calculate that. You need to know which direction is the wind going, and it is in the direction of wind, that is implicit in the problem, it is not said anywhere in the problem, as we mentioned yesterday. Second example, so here we said 50 meters cross wind, which means that y is not 0 anymore, y is off the x axis for 50 meters away. So, we put y is 50. See, in some cases it is not clear. So, most of the times when you are doing the problem, this is not important, people are not, this is only an examination, people give cross wind, center line and all that. We will see what the real application is, we do not care about all of these things. We are interested in finding out a lot of points, we just calculate everywhere and find out what it is. So, this is just from a single, if you are writing an exam, somebody will ask you what is center line or what is crosswind, that is important, but otherwise in real situations we do not use these kind of calculations. We do not use it for this kind of, we are not just interested in center line. So, how do we apply the dispersion model? So, the estimation of what we are using it for is estimation of pollutant concentration at any given set of coordinates, whatever it is. Then we assess the impact of one source on air quality. We can also assess from a large number of sources. We just add a large number of sources. For example, if you are interested in doing a large number of sources, so I am looking at a top view of a map, okay, there is a source here, we will call it as source 1, and this source 1 has a plume. Source 2 somewhere nearby, and if assuming that wind is in this direction, source 2 also has a plume, source 3 also has a plume, yeah. It may have different Q, Q1, Q2, but what we are assuming in dispersion model is, let us say if I want to measure the concentration at this point, some location x, y and z. Now there is a contribution from source 1 because this is S1. There is also a contribution from source 2. There could also be a contribution from source 3. All of these 3 will contribute to concentration here. In the model we just add all of them, that is it. Now we have a frame of reference. If we assume this to be origin, we assume this to be origin x equals to 0 or something, we will just take this as the point of reference and everything else we will calculate from here. So in the dispersion model when we are assuming this, we can transpose all of this. Even if we do the calculation for this, we add this contribution to this based on a set of coordinates based on one of them. So when you are doing the calculation, this is x, right, this is some y, this y is different for this one, this y is different for this one, this y is different for this one, each one of them the y is different, okay. But in the real system y is y, there is one fixed coordinate, right. But when you are doing the calculation for individual sources, you have to transpose that, you have to adjust that y. So you take the frame of reference, a fixed frame of reference for the point, and then this one you have to do it separately like this. I am not sure if I am clear on this, but when you do 3 sources you will know what we are talking about. So contribution to this source from a particular the application, when we do this we define a grid of measurement coordinates also called as receptors. We say receptors, what we are doing is we are trying to measure concentration, exposure, which means there is a receptor there. So we are, instead of receptors, what we are doing is we are putting the coordinates x, y and z on the left hand side of the Gaussian dispersion model, that is a receptor, which means it is a coordinate, and we define a grid of coordinates. We can calculate this, the source, the concentration at those coordinates for y as a set of coordinates, a large set of coordinates, and we estimate the emission rates for all sources and location with reference to some origin. So as I described earlier, we estimate meteorological parameters, we also estimate concentration of pollutants of all receptors. Once we do this, you have to represent it somehow. So there are a large number of sources, is there one source, even if there is one source. I will show you the example for one source. How do we effectively represent this? Okay, the way we do it is by mapping it. So this is a very good way of doing it. So for example, this is a map of Chennai and this is a garbage dump in South Chennai. Okay, this is a source. I am assuming this is my source, one source. So if I measure a large set of coordinates all around this, I am assuming that the wind is coming from this direction. If my wind is in this direction, I am defining that as my x axis, and then I am measuring it in a wide set of coordinates. I can have a Cartesian grid. I can just define a bunch of this entire zone. I am measuring the concentration, say at 100 locations. Then I get a table of concentration versus coordinates. Then there is, what we do is this, we join the lines. It is like an isobar, an isopleth, what is called as an isopleth. An isopleth is the line joining points of equal concentration. So this gives you a contour map. So here I have written down contour map. This is a source, very close to the source. This boundary of the source, this radius around the source is 100 micrograms per meter cube is the concentration of some pollutant. So you are going out, you are expecting concentration to decrease. So this contour is 80, this contour is 50, this contour is 50, this contour is 40, and so on. So you get a map of where the pollutant is going. You get a visual map of where the pollutant is going. So this is the superposition of your Gaussian dispersion model calculation with reference to a real source. So on a map, this is how people apply this. On a map you have different sources, there is only one source. Now I can have multiple sources, I can have source 2 here, source 3 here and whatever. And I do not have, I can just put a contour map of one particular pollutant. So the contour map is for one pollutant, because the pollutant concentration depends on the emission factor and emission rates. So So, even if they are burning coal in all these 4 places, the emission factor for sulfur dioxide, if they are doing the same process, it should be the same, but you still have to estimate it differently for all these 4 sources, depending on the emission rate is estimated differently based on activity rates and all that. So, each of these things have done separately, and then you apply the Gaussian dispersion model and then plot what is going to be the contour map. So, what this gives you is application is, let us say that you say that 50 milligrams per meter cube is the ambient exposure level. You can't, anything above 50 is supposed to be not safe. So, then you can say that I will mark these regions in this radius to be seriously affected. So, this is very useful in planning or emergency response. So, say you have to evacuate, say there is a leak, there is a factory and there is a leak, and this leak happens, and immediate response you want to say who are the people going to be affected immediately, and you can say this is a radius worst case scenario. Worst case scenario means very low wind, very high wind, dispersion happens very fast. You have to find out what is the worst case scenario, run the dispersion model and find out which case is the lowest. So, you have to map these things. So, there are companies that do this emergency response planning. So, they will have scenarios, they will have worst case scenarios. We know the wind rows, we know the behavior of wind, and we know extreme events. They say there is a big cyclone and something happens, and so for different events they will have different plans. So, if they know, if something happens, they know exactly what to do, which area should be targeted first, and if you know that area is going to be under high risk, you give them some safety equipment, says if there is a leak, please put on this mask or stay indoors or something, whatever, do something, do some remedial measure if you are unable to evacuate from there. So, this is emergency response measures. Dispersion modeling can give you a great deal of. The second type of application, in sense how you can use this information is to plan the siting of industry. This is a very common thing, and the reason people used to do this very heuristically. So, you have these industrial estates, or this, what we call as this in India we have this, in Tamil Nadu we have the SIPCOT, small industries system. So, they are all located in some places which are far away from typically urban places, and the idea behind that is given the wind patterns and all that, even if there is an emission something, there is nobody downwind that will get exposed to it. So, it is essentially away from, it is far away from all exposure, all receptors. Okay. If you do not take that into account, this is why you see a lot of debates, right. Where do you cite a particular thing? They say it is dangerous, you can't put it here because it will cause groundwater pollution. The same thing, what we are talking about air here applies to other media as well. We are talking about soil pollution, water pollution and all that. We do not want things to reach a receptor, or reach, by the time it reaches, it should, concentration should be small enough because of dilution or dispersion. So, these models give you, the mathematical models give you a very good preliminary handle on this. What we talk of preliminary handle is, it is not accurate, by no means it is accurate, but it gives you a general idea that 5 kilometers is a region that is of going to be great interest, worst case scenario. If it is better than this, fine, very good, no problem, but it is worst case scenario what we are planning for. Dispersion models are reasonably good under these conditions. So, you can also plan in, you can, the way you apply the dispersion model depends on whatever you are trying to do, your objective. Okay. There are a lot of companies which do this, it is very common in the West, it is catching up here, people are trying to find out scenarios in urban areas. For example, there are a lot of places in India where right now there are industries in the middle of a large city. For in Chennai itself, it is supposed to be in the outskirts, now around that there is a lot of residential areas. It has happened in all cities in India. There is large amount of urban residential locations, in the middle of that there is a cluster of industries. So, therefore, the regulation and the way they operate and all that comes under scrutiny. There are a couple of small artifacts to this dispersion. These are the non-idealities. One of them is called as stack tip downwash. Now, this is not important for ambient pollution, but it is important for in the place, in the source. For example, you have a factory and you have a stack you have a chimney which is releasing emissions. Okay. There is a possible scenario that this plume will not disperse, but it will come back right below next to the stack. So, the reason for this is the same reason why particles get absorbed. So, the wind is here, the streamline of the wind goes around the stack, the wind flows around the stack. When that happens, there is a low pressure region that is created here right behind the stack. Because it is low pressure, if anything comes in this region, it gets sucked into this low pressure region and it circulates there, it keeps circulating there. Okay. Why does this happen? It happens when you the material coming out of the stack does not have enough momentum to clear out of this region. So, it happens only when the velocity of the stack gas is smaller than the wind, very small. So, what happens is as soon as it comes out, it gets pushed in, it gets pushed to the side and it can get into this low pressure zone and it can recirculate there. So, when this happens, this stack this region, the concentration of rho A1 can increase, can accumulate over a period of time. So, which means that for exposures of people standing here can be very high. So, in plant exposure can be very high. So, that is not very safe for the plant whoever is working there. So, to avoid that, people have a recommendation that the stack velocity, the gas velocity coming from the stack must be at least 1.5 times greater than the wind speed at that point. The stack here, this is the ux at the stack. So, the ux at stack should be greater than the velocity of stack must be 1.5 times greater than the this much, by this much. The other type of artifact is called as the building downward. This is more serious. This affects people away from the source. So, there is a streamline, these dotted lines are streamlines, and you see a big building in the pathway, the streamline move around it and they create these regions around the building called as wakes, same as the stack tip downwash, but this is huge. Stack is just a small thing. The reason we say stack means many of these industry stacks are huge, they are not like 20 centimeters, they are big, several meters in diameter and all that. So, at least at ground level, so these buildings can be big. So, these buildings, the streamline separation around buildings causes these low pressure regions called as a wake, it is called as a wake. And now if there is a plume that is going here and this plume gets near the wake, it can get sucked into this wake. So, it can get pulled in and it will recirculate here over a period of time. That is one. Second problem, suppose you have a stack on top of this building. If because this region marked by this red line, the red curve is not part of is inside the wake, which means it is not mixing very well with the outer this thing. There is no air circulation in this, there is no air movement here. If your stack release is right on the roof of a building and there is a height of this wake, there is some distance, there is the length of the wake. Depending on the size of the building, these dimensions form, okay, and the velocity of the. So, if this stack is below this height, it will not get out, it will stay there. This entire thing will accumulate in this region around the building. It can sink in, it will just accumulate there, concentration will be very high, which means its exposure to people in the building or near the building can be high. The only way to do this, you have to extend here so that it gets carried by the general wind, that is crosswind that is happening, and so then it will disperse nicely. This can happen in a lot of buildings which are not planned. Can you give me an example of this? Stack on top of a building which is not extending into the there are a lot of examples, you can go around seeing dispersion, stack tip downwash, building downwash, small sources. What is one of the major urban sources of emission, combustion sources that you can think of? Not vehicles, other stationary sources. Kitchen is one. Second, there is one more source. So, kitchen is one very good example. So, a lot of these big corporation offices, they have a food court or something and they have a long chimney that will be rising it will go to the roof and stop here sometimes, and you can see in some of the buildings nearby there will be a big black mark in the top part of the building, which is indication that it is not gone out, it is there. It has to extend further up. That is a cost, because you have to pump all this exhaust a few meters high. Pumping is expensive, okay, you have to work against this thing. So that is a cost, so people do not plan it ahead. That is one. Second, what is the second source? Large buildings, you can see it. You can see it in the research park here, next to research park, the IT park. What is one common source of combustion that people use in current urban scenarios in India? So, it is a generator, it is a diesel generator people have, huge diesel generators. You can see in buildings, a lot of residential buildings have it, a lot of commercial buildings have it. There is an exhaust, and diesel generation, diesel exhaust is considered to be diesel engines have a very bad history with exhaust, so it is improving now, but a lot of fine particulate matter that comes out of it, and this diesel exhaust supposed to go all the way. If you follow the rules of dispersion, proper dispersion, you have to, stack height has to be reasonably high. So, but if you are in the middle of an urban cluster, where will you send it? You have to send it out really high, because there is building downwash, it is not going anywhere, everything is accumulating in the road, it will stay there, a lot of carbon dioxide, it will sink, and it will, road level pollution will be very high. So, it is supposed to go out all the way up into the region above the wake and get out, disperse. A lot of times it is not done. So, this design of these kind of devices has, we use dispersion models, and we use these kind of these things to do this.